Hi, it's Miss House. I wanted to give you some background information on section 3.2 in order to help you with this section. In this section, we'll be studying logarithms. And the most important thing for you to try to keep in mind is that a logarithm is an exponent. It's a specific exponent that you raise a base to in order to get a certain result. So, for example, if I raise 10 to the 0 power, I get 1, because anything to the 0 power is 1. If I raise 10 to the first power, I get 10, because that means 1 factor of 10. If I raise 10 to the second power, I get 100. And I could continue this way. 10 to the third is 1,000. But what if I want to raise 10 to some power and get 50? So you may think, well, that's not possible, but it is. If 10 to the 1 is 10 and 10 to the 2 is 100, then this value has to be somewhere between 1 and 2. 2 is too big because you get 100, and 1 is not big enough because you get 10. So this is the process of taking a logarithm. So when I want to know what is the exponent that I raise 10 to get 50, I take out my calculator, okay, and I type in 50, and I press the log button. Now notice the value that came up was, let's see what that is, about 1.699, okay? Now this is an approximate value, 1.699. Now you'll notice that there are a lot of decimal places past this, and I might want to go a little bit farther, but 3 decimal places is probably what my math lab is going to ask you to do. Now, if this is in fact the answer, that means if I take 10 and I raise it to this power, I should get 50. So let's try that. 10, let's see, let me clear this. Base of 10, okay. Raise 2, that's the exponent key. 1.699. Now remember, I rounded this, so I'm probably not going to get 50 exactly. And look, I got 50.0, just a little bit bigger than 50 because I rounded up, okay. So look, 10 to this power does come out to be 50. That is called taking the logarithm, okay? The logarithm is the exponent that you raise a base to get 50. Now, on our calculator, when you have the LOG key, that is always base 10. Now, we also have another key on our calculator, and that is the ln key, and that's the natural log. So ln means natural log, and that's a base of e. And we've talked about e, and remember that base e is just approximately 2.7, okay, like pi is 3.14, e is about 2.7. These are the only 2 bases that these 2 keys will do on your calculator. So at a later time, we'll talk about how you can find, for example, a base of 2 to some power gives you a certain outcome. We can use logarithms to do that as well, but we have to have a formula for doing that, and we will talk about that later. Okay, so keep in mind that the logarithm is just an exponent. We're looking for an exponent that we raise a specific base to in order to get a certain result. In the case of base 10, we can use the log key on our calculator. In the case of base e, we can use the natural log key. All right, so let's do some of these problems from the homework. But before we do that, okay, so let's talk about another aspect of logarithms. Let's say I have y equals 2 to the x. Now this is an exponential function because The unknown, the variable, is in the exponent. If I want to draw this graph, you did some of these, I hope, in 3.1, I can make a little chart, and I could pick a few values, okay, and then I could find these values. 2 to the 2 is 4, 2 to the 1 is 2, 2 to the 0 is 1, 2 to the negative 1 means take the reciprocal. And if I graph this guy, it looks like this, okay? Now, we talked about functions passing the vertical line test, right, which this one does. And we talked about one-to-one functions passing the horizontal line test, which this one does. And since this passes both the vertical and horizontal line test, this graph, this function, has an inverse function that undoes it. This is in 1.8. That's going to be a reflection across this diagonal line, y equals x. So it's going to look like this, right? Because it has to be exactly the same on each side of this dashed line. Well, let's look at the process of finding the inverse of this function. So in 1.8, we talked about finding inverses, and we said that in order to do this algebraically, you switch the x and y, so I would write x equals 2 to the y, and then you solve for y. But we don't have a way to solve for this y, except now we do. What we can say is, remember the exponent, the log is the exponent, okay? So the log is the exponent that you raise a particular base to, the base is 2, to get a certain result. And so this is the way that we can write this function solved for y. That's 2 to the y equals x. So our first conversion formula is, if you have log base b of a equals x, you can write that base to the exponent equals the answer, which is sometimes called the argument of the log. So look at this conversion. Little b, okay, this little number is the base. Now, if no base is written at log, that means that the base is 10, and we don't have to write it, just like we don't write an exponent of 1. Okay, log without a base written is understood to be 10. But if we don't know what the base is, we'll just call it b. A, the argument or answer, is here, and the log of this is equal to the exponent. Because remember, the log is the exponent, right? It's the exponent that you raise a certain base to get a certain result. So the base is the little number. This number that's isolated by itself is always the exponent, and this number that we're taking the log of is the result that we're trying to get. All right, so using this fact, this is important, okay, that's your conversion. This is why it works, okay, because these are inverse functions. Using these facts, we can now look at our homework. So, first one says, write the equation in its equivalent exponential form. So the little number is the base, 4. It's equal to the exponent, 2, and the answer or result we wanted to get is 16. So look, base to the exponent equals the answer. And that makes sense. 4 to the 2 equals 16. Number 2, base is the little number, 2. The number that's isolated all by itself is the exponent, 5. And this bigger number in the log, the thing you're taking the log of, is the answer or argument. So 2 to the 5th equals m. 3, 2 to the 5th equals m. Here, the base is the little number, b. The number by itself is the exponent, 2. This number is the argument. That's the answer that you get when you raise a certain base to an exponent. Now, don't let the negative numbers and fractions throw you off, okay? In this case, we're going in the opposite direction. So we're going to have to take the log. The base is the number being raised to the power, so in this case, it's a little 4, okay? The answer is the thing that's by itself, and this has to equal to the exponent. Remember, the log of whatever you're taking the log of has to be equal to the exponent, okay? Now, if you have a square root, something that you may not remember, but when you have a number that's to the square root, it can be written with a fraction exponent, 1/2. So the square root of n is 1/2. So if we want to write this, we would say 25 to the 1/2 equals 5. And then we can write it with an exponent. We can write it with a logarithm by saying the base is 25, so log 25 has to be equal to the exponent of 5. So the log base 25 of 5 equals 1/2. What do you raise 25 to get 5? It's 1/2. This one, y to the 5th is 1,044, would be log. Our base is y. Our result is 1,044. It has to be equal to the exponent, which is 5. So remember, in the log expression, it's always equal to the exponent. Here my exponent is c, so I know it's going to be equal to c. So it's log, the base is 9, of 120 equals c. And later on, we'll learn how to find these answers. 9 to what power is 120? But right now, we're just writing in our exponential and logarithmic forms. Okay, now we've got to find the exact value without a calculator. This is a little bit tough. So we're asking 7 to what power is 343? Now, since the number's big, it's not really realistic to find this without a calculator, but if you do 7 to the 1, you get 7. Do 7 to the 2, you get 49. And when you do 7 to the 3rd, you get 343. So the answer here is 3, because 7 to the 3rd is 343. And if you don't know that, of course, you'll have to use your calculator to find your exponents here. All right? Now, another thing to remember that you may have forgotten or just have never seen is, what can I do with this 136? Okay, so I'm going to use my understanding of exponents to rewrite this. 136 is 1 over 6 squared. Now, I know I need to use a 6 because, look, base of 6. And this is 6 to the negative 2. Because remember, the negative means take that base and put it in the denominator. So now, what they're saying is 6 to the negative 2 is 136. That's true. So my answer is negative 2 because the log is looking for the exponent. Here we have this square root of 7, okay? So the square root of 7 is 7 to the 1/2. So they're saying, what base do you raise 7 to get the square root of 7? The answer is 1/2. Number 11, we have 81 to some power has to come out to 9, okay? Well, the square root of 81 is 9, so we have to say, what is the exponent for that? Well, that's 81 to the 1/2. So that is also 1/2. In number 12, what power do you raise 4 to get 4? Well, that has to be a 1 because 4 to the 1 is 4. Number 13, we have a base of 8 raised to some power equals 1. Well, anything raised to the 0 power is 1. Okay? And for this one, log number 14, 7 log base 7 of 4. There is a property for this, which would probably make this easier. If you have a base raised to a log of the same base, okay, it's going to be, the argument is going to be your answer. And that has to do with the properties of inverses. So just remember that when you have a base, let's do that one again. So when you have a base raised to a log of the same base, okay, the answer is just whatever the argument of the log is. Okay, and again, this has to do with inverse properties. And so in this case, the answer is going to be 4. All right, now we're going to do some graphing, and I'm going to switch over to my math lab to do that, to show you how to do these graphs. Okay, and it's going to be very similar to the way we did the graphs of exponential functions, where you have to put in the exponent, where you have to put in the asymptote, I mean, in order for it to give you credit. Okay, so this is the graphing in section 3.2, and that starts with number, let's see, number 15, okay, so 3.2, number 15. I've already done this in another class, so I'm just going to ask for a similar exercise. Okay. All right, so let's make this where you can see it. So they're asking us for the graph of the log base 4 of x. Now, I could do this manually. Okay, so let me show you how I do it manually. If I have y equals log base 4 of x, that means 4 to some power y equals x. Okay, now the inverse of this would be switch x and y, 4 to the x equals y, and we know what that looks like because that's an exponential function like this, where you have 1 is 4 and 2 is 16 and so on. You just pick values for x. So our logarithmic function, which is the inverse of that, is going to be the reflection across this line, so it's going to look like that, right? So we could find some values. Remember that inverse functions reverse your x and y coordinates. So if I do 4 to the x, I get 1/4. If I put in -1, I get 1 for 0. 1 is 4, 2 is 16, because I'm raising 4 to the power -1, to the power 0, to the power 1, to the power 2. Well, these are going to all be reversed on the inverse because that's what the inverse function does. It reverses your ordered pairs. So at 1/4, it's down here at -1. At 1, it's at 0. I didn't exactly get that point drawn perfectly here. At 4, it's at 1. At 16, all the way out here at 16 before it gets to 2. So you get an idea of how we could do this manually, right? by looking at the inverse first and then reversing those ordered pairs. Now, the way we do it in my math lab is click on the graph, okay, and look, you've got, this is the old one, the exponential, right? Okay, that's not the one we want. We want the logarithmic, which is this kind of curve, and it doesn't matter where you click, it's going to put it down here, okay? And it's got a base of 4 already, and then we look at our shift. So look, x plus 3 is on the inside of the function, so that's going to be to the left 3. So we put a minus 3 there. Now watch what happens when I click. It moves it over minus 3. Now normally, look, this x, or this y-axis is your asymptote, right? This y-axis right here is an asymptote for this logarithmic function. So we have to put in our asymptote, but it's been moved to the left 3. So our asymptote is going to be a line that's dotted, and it's going to be at negative 3. So look, I go up here and I look at my order pairs till I see a negative 3, and I plot 2 of those, and then I save it, and it will give me the correct answer as long as I put in the asymptote. Now it's going to ask for the equation of that vertical asymptote, and you have to put x equals negative 3. Has to be an equation, okay? And the domain, now here's the difference. In the domain, look, our x value only goes close to negative 3. So it doesn't include negative 3, because that would make a 0 in your argument, and you can't have that, okay? This argument of your log has to always be a positive number, okay? But it goes to infinity, okay? And you can tell that by looking at the graph. Look, it comes close to the asymptote but never touches it, but it goes to the right forever. And it'll ask you what the range is, and look, the range is from way down here, and then this slowly creeps up over time, so it's going to be from negative infinity to positive infinity. So you're going to use shifting to do these just like before. Now in this case, since the minus 5 is on the outside, okay, it's not in the log. If it was, it would have parentheses around it. It wants us to, let me go back to that. It wants us to let me finish this because I did this in another class, and then we'll come back and we'll do a similar one. Just 1 second. I want a fresh problem. Oops, the domain. Oh, it's from 0, sorry. And the range is going to be negative infinity to positive infinity. Okay, so let me go back. All right, similar question. Look, this is going to shift the whole thing down 4. So I'm going to click to enlarge it. Look, I'm going to click on the logarithmic tool, anywhere on the graph. I'm going down 4 because it's not in the log. If it was, it would have to have parentheses around it. So I'm doing a vertical down 4, so negative 4 on the vertical. Okay, and when I do that, look, it shifted it down 4. Save that. Now, I'm going to miss this. Watch what happens. I forgot the asymptote, so look, when I check it, it's going to give me some hints, so I've got to fix that by putting in the vertical asymptote. Now, this time, we didn't go to the left, so our vertical asymptote is the y-axis, so we just click that line, dotted line, a couple there, save it, and then we check our answer. Okay? So the vertical asymptote is x equals 0 because on the y-axis, x is 0 everywhere. And the domain of your log is going to be negative, the domain is going to be the x value, so that's from 0 to infinity in this case. And our range is going to be from negative infinity to positive infinity. All right, now, when you get to graphing the natural log, remember the base is e. That's going to automatically be included here. So watch what happens. When I do this, it shows the base is e, okay? So I don't need to change my base. It's going to do it for me. This x plus 4 is on the inside, so we're going to the left 4, so that's going to be a horizontal minus 4. There it goes. Now we're going to put in the asymptote. So the asymptote got moved over to negative 4. And I need that to be a dotted line, so I'll do dotted line, and I'll check my answer. So don't be thrown off by the natural log. It's just a base of e instead of whatever base they gave us before, which was a 4 in one of our examples. So the vertical asymptote in this case is x equals negative 4. And the domain is from, you can tell, negative 4 to infinity. And we never actually get to negative 4 because that's an asymptote. We approach it. So make sure you put a parentheses there. And the range of all your logarithmic functions are going to be from negative infinity to positive infinity. Remember, the exponential function's domain is negative infinity to positive infinity. And this one is going to be the reverse of that. So if the domain of exponential is negative to positive infinity, the range of the logarithmic is negative infinity to positive infinity. Okay, and so you can continue to do these. The domain of a function that is a logarithmic function, this has to be greater than 0. So what you would do is you would say whatever the argument of the log is, x plus 2 has to be greater than 0, so x has to be greater than negative 2, that's negative 2 to infinity. If you think about it, this is shifted to the left 2, right? So negative 2 to infinity. Okay. The domain of this one, again, f of x is the log of 15 minus x. This argument has to be a positive number. So we say for this one that whatever's in the log, what you're taking the log of, 15 minus x has to be greater than 0. 15 has to be greater than x. That means x has to be less than 15. Look, if you put something bigger than 15, you're going to get a negative in there. So less than 15 is negative infinity to 15. And if we were to graph this one, it's going to go in the opposite direction because, look, there's a reflection in there. Okay? So from negative infinity to 15. All right? Let's look at that graph just so you can see. Let me go back. The log of 15 minus x. Let me do this in Desmos real fast to show you. Y is the log of 15 minus x. All right, see this guy? So it's from negative infinity to 15. It cuts it off, but it's not, technically, it's not a vertical line. Remember, it's approaching this asymptote here at 15, okay? And that's because, look, there's a negative in front of the x. That's a reflection across the y-axis. So instead of going the other way, which most of them have done, it's going to be going this way from negative infinity to 15. All right, let's see, am I? Okay, a couple more. Evaluate the expression without a calculator, okay? So in this one, we just use our knowledge of exponents and powers of 10. Although you can do this one on the calculator, because look, that's a base 10. So you can press log of 1,000. Okay, so you put in 1,000, you press the log, and you get 3. Okay, well, that's because 10 to the third is 1,000. Okay, remember, when you're doing a log, you're looking for the exponent that you raise, whatever the base is, understood 10 here, to get that answer there. This one, 10 to the log base 10 of 40, that's that property we talked about. And that is if you have a base to a log of the same base, some argument, some answer, it's almost like those cancel each other out because they're inverse functions. The exponential and the log function are inverses, and they cancel each other out. So the answer to this one is going to be 40. That's one of the first properties about logs that we learn, and we'll learn some more in class on the next class. Okay. Now this is the same. This is e to the 4th, but remember the base of the natural log is e. So this is saying, what do you raise e to get e to the 4th? So that answer is going to be 4. Okay, and you can think of that as go back. You can think of this as, remember, the natural log is a base of e that we don't write. So it's really this, log base e, okay? And they're saying log base e, pull this down where we can see it, e to the 4th equals some unknown power. So what do you raise e to get e to the 4th? Well, that means x has to be 4 for these to be the same. Okay, the next one. This is the same property where we had log or 10 to the log base 10 of a number, or base to the log base b of a number. Well, this is the same thing because it's e to the log base e. Remember, that's understood. So this is going to be 113. These are inverse functions, so they undo each other. Yep. No problem. I'll turn off the lights as soon as I leave. Yep. Sorry, they're getting ready to run me out of here. Check answer. And then this one, look, e to the ln of 4x squared is going to be 4x squared. And so that is an overview of the exercises in section 3.2.